This is part 8 of the series Circles, and we're going to begin this part with a new theorem, the angles inside a circle theorem. And the angles inside a circle theorem says if two chords intersect inside a circle, then the measure of the angle formed is 1/2 the sum of the measures of the arcs intercepted by the angles. So the measure of this angle is going to be equal to 1/2 arc AB plus arc CD. Notice that this angle intercepts arc AB and this angle intercepts arc CD. Also notice this point, the point of intersection of the two chords, is not necessarily the center of the circle. It's not required that it be the center of the circle for this theorem to work. Alright, it's a fairly straightforward theorem, but it's important to keep straight what's going on. So let's take a look at the proof and see if we can figure out how this thing works. So what we're going to do is show that angle 1 equals 1/2 AB plus CD, given that AC and BD intersect inside the circle. The first piece that we're going to do here to do this proof is we're going to establish some new information by drawing some auxiliary lines. We're going to draw an auxiliary line between BC and AD, and we're going to create inscribed angles. And we're going to use the relationships of those inscribed angles to relate this angle to these arcs. So let's go ahead and draw in our information, put in our givens, and generate an overall plan for this proof. So we've drawn in our given, and we've drawn in segment AD. That establishes angle 2 as an inscribed angle which intercepts arc CD, and angle 3 is an inscribed angle that intercepts arc AB. So we know that the measure of angle 3 is going to be 1/2 AB, the measure of angle 2 is 1/2 CD, and because angle 1 is exterior to this triangle, you know that the measure of angle 1 is the measure of angle 2 plus 3. And thereby we can create a relationship between angle 1, 2, 3, and ultimately these two arcs. So our first statement is going to be that this angle is 1/2 this arc and this angle is 1/2 this arc. We have the measure of angle 2 is 1/2 arc CD, and the measure of angle 3 is 1/2 arc AB. Now we're going to go ahead and relate angle 1 to angle 2 and 3 so that we can establish this relationship, because I have to have an angle 1 on one side of the equal sign and I have to have these two arcs on the other. And angle 2 is related to CD, angle 3 is related to AB. Always keep in mind what it is you're trying to prove, and you try to form those statements as you go through your proof. So that's our next step, is to relate angle 1 to 2 and 3. So we've got the measure of angle 1 equals the measure of angle 2 plus the measure of angle 3. That's the exterior angle theorem. So angle 1 equals 2 plus 3. Now we have an angle 1 on one side, angle 2, which is related to CD on the other side, with angle 3, which is related to AB. What I need to do now is to substitute this for angle 2 here, and this for angle 3 here. And that will give me expressions with CD and AB, which is what I need up here. So that's my next step, is my substitution. Now we're really close to what we need to be at. We have 1/2 CD and 1/2 AB. The only difference between this statement and this, other than the order, which order doesn't really matter here because addition is commutative, is to distribute this 1/2. So we're going to factor this out, which is the distributive property. And when we factor out the 1/2 from these two terms, we will have our final statement. And now we've just shown that the measure of angle 1 is 1/2 the measure of arc CD plus the measure of arc AB. Now, let's move on and use this in an example to see how this works, and it's a fairly straightforward theorem. In our first example on the left here, we're given AC and BD intersecting inside the circle, forming angle 1, And we want to find out the measure of angle 1, given that the measure of arc AB is 42 degrees and the measure of arc CD is 65. So using the angles inside a circle theorem, we know that the measure of this interior angle, angle 1, or this angle, is going to be equal to 1/2 the sum of the intercepted arcs. So the measure of angle 1 equals 1/2 the measure of AB plus the measure of DC, which is 1/2 42 plus 65. This gives us 1/2 107, which is 53.5. Alright, fairly straightforward use of the theorem. Now let's take a look at another problem. Here we have a slightly different situation. We have angle 1 sitting out here, and these two arcs are given to us. Now you need to be really careful when you use these theorems. Don't knee-jerk and say, oh, because these two angles are the intercepted arcs, that angle 1 is going to be 1/2 this plus this. Because it's not this angle that's 1/2. It's this angle. And so what you're going to have to do is find this angle, and since this is the supplement of angle X, then you'll have to find that afterward. So be very careful that these placements are proper. Notice here it's offset, and here is the one that we're actually using. So make sure you get this straight. X equals 1/2 103 plus 122, which is 1/2 225, which is 112.5. Now that's just X. That's not our final result. You're not done yet. To get the measure of angle 1, we have to take 180 minus 112.5, which is going to be equal to 67.5. So this is actually our final answer, not that. Subtle difference, but it means the difference between getting the answer right or wrong. Alright, let's move on to the next theorem. And this theorem is related, but it's different because the angles are going to be outside the circle instead of inside. Here we have the angles outside a circle theorem. And it looks a little complicated, but it's not as bad as it looks. If two tangents, a secant and a tangent, or two tangents, intersect at a common point outside a circle, then the measure of the external angle, this angle, is 1/2 the difference of the large and the small intercepted arcs. So, this angle is 1/2 the big arc minus the small arc. This angle is 1/2 the big arc minus the small arc. This angle is 1/2 the big arc minus the small arc. So it's a fairly straightforward theorem, but there's three separate cases to it, and so it may appear a little different. The theorem works exactly the same. The outside angle is 1/2 the big minus the small. Always, always. Alright, let's take a look at the proof of these, and there are three cases. We're going to start with the two tangent case. So let's go ahead and take a look at that. Here's our setup, and what we're going to do to plan for this proof is we're going to draw in an auxiliary segment here, and then we're going to relate these angles. So let's go ahead and draw in our givens, our auxiliary segments, and additional information, and then let's come up with a plan for our proof. So here we have segment BD, and we've created angles 2, 3, and 4. And we're going to use the tangent intersected chord theorem to show that this angle is 1/2 this arc, this angle is 1/2 this arc, and we're going to relate these two angles, angle 1, 3, and 4, by the exterior angle theorem, because with this triangle, that angle is exterior. So that angle is equal to these two angles put together. So that's the general overall proof, because we have to relate angle 1 on one side, BCD and BD on the other, and so we have to have this relationship between BCD and that angle and BD and that angle. So let's go ahead and start with our first statement. This is 1/2 this, and this angle is 1/2 this. We've stated that measure of angle 4 is 1/2 arc BCD, and the measure of angle 3 is 1/2 arc BD, and that's by the tangent intersected chord theorem. Now we have a relationship between angle 4 and BCD, angle 3 and BD. Let's go ahead now and establish a relationship between this angle and these two angles. We can see that angle 4 is now equal to angle 1 plus 3. So this exterior angle is 1 plus 3, and that's by the exterior angle theorem. Now what we have to get to is a form where we have angle 1 on one side and something relating BCD and BD on the other. Well, here angle 4 is BCD and angle 3 is related to BD, but we have angle 3 and angle 1 on the same side. So what I'm going to do is I'm going to move this over to this side. So I'm going to subtract out the measure of angle 3. We've used subtraction property of equality to subtract angle 3 from both sides. And now you can see we have angle 4 and angle 3 on one side and angle 1 on the other side. And if you notice here, angle 4 is an expression of angle BCD, and angle 3 is an expression of angle BD. And that's what we're looking for. So we need to make this substitution now. We're going to substitute this expression for angle 4 here, and this expression for angle 3 here. Now with this substitution, we've gotten very close. We have BCD and BD on one side, and the measure of angle 1 on the other side. It really doesn't matter that angle 1 is on the right and here it's on the left, and this is on the left and here it's on the right. It's a simple matter of the symmetric property of equality. What is important is the fact that we have BCD and BD together. The only difference between this and this is that here we have factored out the 1/2. So that's what we're going to do next, is factor out the 1/2, and we will have our final statement. So here we have the measure of angle 1 equals 1/2 BCD minus BD. And that's distributive property and the symmetric property of equality. And we've got our proof. In the next part, we're going to go ahead and prove the other two cases. And those are the secant and tangent case and the 2 secant case. And you're going to see that those two cases are very similar to this proof, and you're going to see very similar results. So I will talk to you in the next video.